Hello everyone, and welcome to Python Programming Practice. In this episode, we are going to be covering LeetCode number 509, Fibonacci Number. And this is considered an easy problem, and it's also a problem you tend to see quite a bit in introductory programming courses, so it's not something exclusive to LeetCode. They just happen to have it on here as one of their problems, so we're going to do it through here. So we'll start by reading through the problem directions and the examples, and then we'll get into coding up a solution here. So the Fibonacci numbers, commonly denoted capital F of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. That is, f of 0, so the Fibonacci number of 0 is 0. The Fibonacci number of 1 is 1. And then for every Fibonacci number after that, it is the sum of the two preceding numbers. So, for instance, if we wanted f of n, if we wanted to plug in 2 there, so to get f of 2, we would just add the two preceding ones, which here we see is 0 and 1. So f of 2 would also be 1. So the problem is calling for us to, given a number n, calculate capital F of n. So it's asking us to find the nth number in the Fibonacci sequence. So we'll look at a couple of the examples here. So in the second example, we're checking the third Fibonacci number, and the output of that was 2, because Fibonacci of 1 is 1, and Fibonacci of 2 is 1. 1 plus 1 equals 2. And then the third example is to find f of 4, and that would just be what we just calculated, 2. So f of 3 was 2, and f of 2 was 1, so that's 2 plus 1 is 3. So f of 4 would be 3. And there's a helpful note actually at the bottom here. Note that we're only going to be asked to find n's between 0 and 30. So that is helpful to know, because if you're asked to find a Fibonacci number that's very large, the numbers can grow quite quickly, and you can run into some problems with that. So it looks like we won't have to worry too much because we're capped here at 30 on the top end. So let's pull over to the code editor now. So we're actually going to solve this problem two ways. We're going to use a basic recursive solution, and then we're also going to use an iterative solution that will build up a solution and store numbers in a dictionary, which should be faster than the basic recursive solution. But this Fibonacci problem is a very common problem to work with when you are first learning about the concept of recursion in programming. So if you don't know what recursion is, it is a self-referential function. So a function that calls itself in order to work toward or build up to a solution. So in the case of Fibonacci, it lends itself very naturally to make a recursive solution, because the solution for the Fibonacci number at n is equal to the solution of the Fibonacci number at n minus 1 and n minus 2. And we know that there's a base case of the Fibonacci of 0 is 0, and the Fibonacci of 1 is 1. So we can use recursion in order to build up a solution. So let's see how that would look in code. Now, when you're doing something recursively, you need to provide a base case that the function will eventually reach, so that it can, at some point, exit the recursion and build up to whatever solution you're making. So in this case, we know the base case is if n is equal to 0, then we just return 0, because that's just given by the problem that n of 0 is 0. And also, if n is equal to 1, we return 1. That's also given by the problem. And if we see any number that's bigger than that, well, we don't know what the actual solution is then, so we have to return something else. And in the recursive case, we can just return the function itself. So we'll call the function, and we'll return the function of n minus 1 plus the function on n minus 2. So this may seem a bit confusing at first glance, so let's just walk through how this would work if we passed in some number. So for instance, if we passed in 2, we would take in n is 2, we'd check n equal to 0, no, because it's 2. Is n equal to 1? No, it's 2. So then we hit this return. So we'd run Fibonacci on n minus 1, so we'd run it on 1. And we'd also run it on n minus 2, so we'd run it on 0. So this call, when this is run, it would return 1 because n minus 1 is 1, and then this if n equals 1 would actually be true. So this little part would return 1. And then this part here, plus n minus 2, well, this is 0 if our n is 2. So when that's passed in, n is equal to 0, and it returns 0. So this whole thing is 0. So when we run this whole thing on 2, it's going to be 1, this part's 1, plus 0, and that is just 1. So let's say we pass 3 in here instead of 2. Well, this part, self.fib n minus 1, would run fib of 2, which is what we just calculated. So essentially it would break off that subproblem into this part and go as deep as it needed to find the answer, and then build it up and return that here. So this we already just talked about, that would be equal to 1. And then this bit would be n minus 2. Well, we already know what that is, because 3 minus 2 is 1, and the fib of 1 is 1. So in the case of 3, it would be 1 plus 1 equals 2. And the bigger the number gets, the more subproblems that are going to be created. Say, if we had n of 10, well, this call here would run the Fibonacci to find n of 9. Well, we don't know what that is because it's not in our base case, so that would also have to then run n of 8, and that's not in there either. So we kind of get this cascade of function calls, so it'd have to check fib of 7, fib of 6, fib of 5, all the way down until we get a base case, and then it would be able to build up the solution that we're looking for. So unfortunately, that results in exponential number of subproblems in the size of n, which means this solution will tend to be very slow, and the bigger n gets, it could actually result in a program that crashes or just runs forever because it's too slow. But in this case, we're pretty confident that we won't have that problem, because in the problem description, they said we'd only be given n up to 30. So I think we're probably safe in this case, but usually you wouldn't want to do this if you might be handed larger n's, like, say, 50 or 100. It might not work, but this should be okay. So I'm going to hit submit here and see how we do. So let's pull over, and it's judging, but it should be passing soon, hopefully. All right, there we go. So the solution ran in just about a second, and it was faster than 13% of other solutions, so pretty slow, probably competing just with other solutions that were doing this type of recursion. So now we'll go back and figure out a way to make a solution that works a bit better and doesn't need to do all these recursive calls. So we're going to make an iterative solution this time, and we're actually going to store every number that we find and look it up in a dictionary. So let's get rid of this code here. So in our recursive solution, we essentially started with the number we're trying to find and worked backwards toward a base case to build up that solution. So instead of starting with the n we're trying to calculate and working backwards, we can just start from our base case and calculate forward until we reach the n that we're looking for. So what we're going to do is we're going to initialize a dictionary, scene, with the values that we know. So f of 0 is 0, and f of 1 is 1. So we'll use this dictionary to calculate forward, and then when we need to look up what the previous Fibonacci numbers were, we can do that in constant time because dictionaries allow you to do that. So it'll be very quick to look up what n-1 and n-2 are. So all we need to do then is to create a loop that is going to iterate from essentially 2, because that's the next number we don't know yet, up to whatever n is. So we'll say, for I in range 2 to n, we'll do n plus 1 because we actually want to look at n itself as well. We will set the scene dictionary, so scene at I will be equal to scene of I minus 1 plus scene of I minus 2. So since we've already stored scene of I minus 1 and I minus 2 every time, we're essentially just looking those things up in the dictionary, adding them together, and then storing the next one. And we're just doing that over and over again until we build all the way up to the n we're looking for. So not only will this solution allow us to find what we're looking for, it also builds up a dictionary of every single Fibonacci number between 0 and n. That could be useful if we needed to repeatedly look up Fibonacci numbers because we'd already have stored everything up to n, so we wouldn't have to redo all that work in finding numbers smaller than the n we were already given. But in this case, all we have to do is return the Fibonacci number for one number, n. So we're just going to, at the end, return the scene of n. So this should also find the proper answer for this problem, but we've avoided doing all that recursion and simply iterated up to our number n and calculated every single Fibonacci up to that number and stored them. Now, we could have done this without a dictionary and just used variables to do it. It would probably have been similarly fast, but it's good to think about storing things like this because if you were to have to do repeated problems, you could potentially save yourself some extra time by doing that. So let's go ahead and click submit on this one as well and see how we do compared to the other one. I would expect to do better, but not exactly sure. So this time we got 24 milliseconds, so that is a lot faster than our first submission. And we were faster than about 88% of other Python 3 submissions. So I hope you found this explanation useful. If you're interested in more Python 3 tutorials, you could hit subscribe and keep coding.